Okay, good morning. Welcome to Introduction to Photonics. In the last lecture, we had been talking about semiconductor light sources, and we started looking at some of the characteristics of light emitting diodes. So, by nature, we are saying that we are going to be using spontaneous emission of radiation for these light emitting diodes. And we talked about the typical structure being a double heterostructure, wherein an active region which consists of material with lower band gap energy than the surrounding material will be used. So, we talked about a structure as shown in the left side of your screen, wherein the p type and n type are actually made of material with higher band gap energy compared to the p type at the center or in the middle. So, so we can effectively see carrier confinement, and we also said that you choose a material correctly with lower band gap energy, you might also have higher refractive index in that medium, the active medium. So, it ends up confining the photons also in that direction. So we will have photon confinement as well as carrier confinement happening in the active region, and then your light emission will typically happen from one end of this region. So, this sort of structure would be known as an edge emitting LED, right. So, in an edge emitting LED, your let me just make sure we are not getting confused by this. I was actually explaining this from a different context. For an LED, you do not have mirrors at the on either side. So, the light emission is likely to happen like this. Okay. So, since it's emitting from the edge of that structure, we call this as a edge emitting LED. Okay. This is actually slightly different from another type of LED, which is called a surface emitting LED. In a surface emitting LED, you have the same heterostructure with the active region being like this, and you may have the substrate also like this, which may be highly conducting. So, you can use it as an electrode, but at the top what you would have is actually an electrode that is like a ring type of electrode. So, from looking from the side it will look like this, but looking from the top it will look like a ring, and in this case the emission will happen like this. So, it will emit from the surface of the LED. So, well, what is the advantage? The advantage is that your how you define the your electrode at the top determines the aperture over which the emission happens. Okay. In the other case, in the edge emitting case, you can say that light is actually confined within that active region. So, the emission happens only from that active region, and the active region, the thickness of that is typically a micron, in the order of a micron, right. So, the emission essentially happens only from within that region, whereas in a surface emitting LED, other than the electrode, or any area within that electrode, you are going to have light emission, and the light emission tends to be distributed broader compared to what you have in the case of an edge emitting LED. So, surface emitting LEDs are typically they are able to support up to even 120 degree range of angles, okay, whereas an edge emitting LED typically supports about 30 degree range of angle. So, this is about 30 degrees here, and this could be all the way up to 120 degrees. Okay. So, for lighting applications, you would rather have a surface emitting LED, right. So, where you can actually spread the light as widely as possible, okay, and over a larger aperture, because you do not care about the quality of the light. When I mean quality of the light, I should talk about what happens in an edge emitting LED. If you make your active region in the order of a micron, what can you say about the spatial coherence of the light that comes out? So, that is, it is a very small aperture, it is comparable to the wavelength of light. So, the spatial coherence of the light that comes out can be quite good, quite high. So, in this case, you can take a optical fiber, right. You can take an optical fiber and you can place it at the output of that edge emitting LED, and you can couple a lot of light efficiently into the fiber, because the spatial coherence is fairly good from these sources. Okay. So, edge emitting structures are more amenable to coupling into an optical fiber, which may be useful for a lot of applications, like we are talking about LED, but we will go ahead and talk about a laser diode. So, in terms of semiconductor laser diodes, those would tend to be the sources for optical communication applications, long distance optical communication applications. In that case, you need to take light from a semiconductor structure and couple that light into an optical fiber, and from what you have done previously in the semester that if you want to couple efficiently into a single mode optical fiber, you need to have a highly spatially coherent source, right. So, edge emitting LEDs are very good for that, they are amenable to coupling into an optical fiber. Whereas, if you want to just throw lots of light into free space, you do not worry about the mode quality and all that, you just want to cover a large area, you typically go for a surface emitting LEDs. Like these LEDs that are emitting light, these are typically surface emitting LEDs. Do you understand the difference, right? So, lighting applications, surface emitting LEDs. For other applications where you want to couple into an optical fiber, especially a single mode optical fiber, you go for edge emitting LEDs. Now, we talked about the output power as a function of injected current, and we said, okay, we have a fairly linear dependence in terms of the output, and of course, we also said it cannot go forever, because as you inject more and more carriers into the structure and they get confined in that active region, you end up having such high density, carrier density, that you might actually have collisions between the carriers, and that might generate heat, right, and that will reduce the radiative efficiency. What we have actually mentioned, which is represented as eta int in the expression for the output power, and so that may eventually limit the amount of output power you are able to extract from the structure. Okay. So, we will move further into this. One of the interesting aspects that you see here is the output power closely follows the injected current. So, that gives you some ideas, right. So, one of those ideas may be that you can modulate the current that is fed into the LED, and you can expect a corresponding modulation of the output power coming from that LED. Okay. And that gives you some ideas, because now we are using this LED for just illumination purposes, but nothing stops us from modulating the current given to the LED, right. And if it is done at high enough speeds, if you modulate it at 1 hertz, 1 cycle per second, you can probably even sense that the light is actually turning on and turning off. You can see the blinking, but if that is happening at 100 megahertz, right. So, the time period corresponding to 100 megahertz is 10 nanoseconds. Your eye is not going to be able to make out that there is any change in the intensity, right. It will look like constant intensity to us, but it is conveying information. You can start conveying information through that. So, pretty soon we are going to see all these light panels over here replaced by LED panels, right. And in fact, in our street, it was a big event in our street where I live. We had all the street lights converted to LED panels. The local MLA came, and there was a small function where he was inaugurating that thing, and now we have LED lights over our streets. But now that we have LED lights, now we can actually convey information. Now we can modulate that light with some information, and then you can maybe enable downloading of information through that LED lamp, which is primarily for illumination purposes, but now we are enabling communication through that. So, you could have these LED panels changed to this light panels changed to LED panels, and then you could have communication established between that LED panel to your mobile phone. Suppose your mobile phone has some receiver which can pick up that modulated light, then you can send information across that. Okay. So, that is actually a new concept called Li-Fi, just like Wi-Fi, which is wireless fidelity. Now we have Li-Fi, which is based on light, and that is a concept that is picking up around the world. So, people are starting to look at multiple functionality from your LED panels. So, what we want to understand now is, what is the maximum frequency I can support? You understand this, right? Now I am modulating the current, and I am getting a modulation of the light that's coming out of my LED. How fast can I modulate this? What is that limited by? Okay, that's what we want to figure out. So let's actually look into this a little more detail. So we want to look at modulation characteristics of my LED. Okay. To do that, we need to start from the rate equations, and the rate equations here, it corresponds to, in the previous rate equations we were tracking the atomic number densities, right, in the case of rare earth ions, but here what is it dependent on? What number density does it depend on, this light emission? Electron and hole number densities, right. So, I can write a rate equation with respect to that dN over dt, where n corresponds to the electron density, right, per unit volume, which is typically expressed in terms of centimeter cube. So, this I can track. I will say that that is going to be dependent on the rate at which carriers are injected into the structure. So, what is the carrier rate? I upon q, very good. Well, we decided to represent the charge as electronic charge as E, so I upon E, and this is per unit volume. So, I would put that V here, where V corresponds to the volume over which the carriers are injected. So, typically it is the active layer, the cross section of the active layer, cross section area of the active layer multiplied by the length of that active layer, right. So, that is the rate at which the number density is increasing, but it is also decreasing. The rate at which is decreasing would correspond to, if n is my number density, n over some carrier lifetime, right. The carriers would end up either recombining, the electrons recombining with holes, or it could also be lost due to non-radiative relaxation, non-radiative process. So, we can say where 1 over tau c is going to be equal to 1 over tau r plus 1 over tau nr. nr corresponds to non-radiative process, right. You understand that? So, there is a rate at which carriers are increasing and the rate at which carriers are getting depleted. Okay. So, if I were to suppose I drive the LED with some sinusoidal current. So, let us say I have a bias current IB plus, let us say the modulated current amplitude is IM, and exponential of j omega mt corresponds to the modulation. So, it is basically sinusoidal modulation with some arbitrary phase. Okay. So, if I were to go back to this picture here, what I am talking about IB is this value over there. I am biasing at some value and then I am modulating around that value, right. So, if I have that as my driving signal, then I have a corresponding change in the electron density, right. So, once again corresponding to the bias point, I am going to have some DC electron density plus this other component which is varying with respect to time, right. It is a linear process. You inject these carriers and that is going to correspond to the amount of current that is injected into the structure, right. So, now I will substitute these expressions in the above rate equation, and then I will try to simplify. If I try to simplify, I can get an expression for the modulation. Sorry, I made a mistake here. This should be Nm. Right. So, what I want to get is Nm as a function of omega m, where what is omega m? Is the angular frequency corresponding to the modulation. So, yeah, we are tracking only the electron density, but we are assuming that there is a corresponding number of holes that are available. So, the recombination obviously happens with respect to both the electrons and holes. So, whatever is happening to the electrons, we are saying there is a corresponding picture for the holes as well. So, yeah, so if you are injecting a certain current I, right, that is essentially, well, physically it is just injecting electrons, but since the electrons are moving one way, we say the holes are moving the other direction, right. So, we are not double counting that way. It is essentially counting whatever is happening with respect to the electrons. So, we want to get an expression for Nm of omega m, and if we do that, and also the reason we have picked exponential of j omega mt to represent the modulation is because when you do a d over dt of that, you just get a j omega m, right. So, you can substitute d over dt by j omega m, and then you can that simplifies the overall thing that we have. So, if we do that, then what we get is this expression tau c multiplied by Im over E times V divided by 1 plus j omega m tau c. So, all I did is I just substituted the expression for I of t and n of t into the rate equation and replaced d over dt by j omega m, and then simplified it, and just one step from that you will get this expression. This I will write as Nm over 1 plus j omega m tau c, where Nm, or I can also say Nm of 0, this represents the steady state density. So, how do I find the steady state density? What happens to dn over dt if I look at its steady state? That is, I will equate to 0. Then I would just basically have Nm of 0 from that will correspond to Im over Ev multiplied by tau c, right. So, I can just write this as Nm over this numerator, I can just represent a Nm of 0. So, what I want to know is what is called this modulation transfer function. So, I can say that the modulation transfer function h of f is going to be given by Nm of omega m, that is the modulation number density as a function of the modulation frequency, over Nm of 0, which is the steady state. So, you can imagine what this thing represents. At low frequencies, steady state and I mean at DC and quasi steady state conditions, you can basically say that Nm of omega m is equal to Nm of 0, right, because if you are injecting some carriers slowly, you can expect that there is a corresponding change in the output power. Now, I am injecting carriers at much faster rate, right? I want to know whether the number density that I have in this is tracking that, and you can probably physically or intuitively see that as I go faster and faster with my injection, I may not actually be able to catch up because of two things. One is either I'll start my recombination process takes some time, so there is actually some phase lag with respect to the injection, or my non-radiative relaxation happens, and that is also introduces a phase lag. So as you go to higher frequencies, you cannot expect the same number density as you would expect as you have at lower frequencies. But we have an expression for this, and that expression is 1 over 1 plus j omega m tau c, right. That is what we found out in our analysis. Okay. So, if you plot this, if you plot the magnitude of this, so magnitude of h of f as a function of f, what you will find is this represents a flat line and then it is going to start coming down. So, let us normalize this. So, this is corresponding to 1, but we are interested in the frequency at which the modulation transfer function falls off by 3 dB or half. Okay. So, so this is Fm at 3 dB. Okay. So, what you do is you find the magnitude of h of f, right, and that magnitude you equate to half, okay, and once you equate to half, you can actually find out what is Fm of 3 dB. If you do that, what you will find is this 3 dB frequency is going to be given by root 3 over 2 pi tau c in hertz. Okay. So, this is what you call as the modulation bandwidth of my LED structure. And forget about those numeric values, right. Basically, it says it is inversely proportional to tau c, which is quite intuitive, right. So, shorter the carrier recombination time, right, the shorter the carrier lifetime, more will be the modulation bandwidth. So, it does not limit it. On the other hand, if you have a longer carrier lifetime, then that will correspond to a shorter modulation bandwidth. So, if your, for example, if your modulation is due to radiative processes, right, and those radiative processes, let us say the typical values for this thing is tau r is in the order of 1 nanosecond, okay. That is typically the radiative recombination lifetime in a semiconductor. If it is in the order of a nanosecond, so you can say that is going to be corresponding to fraction of gigahertz, right. So, it is root 3 is 1.7 divided by 2 pi, that is probably f3 dB for this is in the order of 250 megahertz, right, something around that. I do not have the exact number here, but that is just giving you a ballpark idea. So, typically hundreds of megahertz modulation bandwidth is possible with these LEDs. Now, I know there is one company which is actually communicating or trying to achieve 60 gigahertz communication. So, they are trying to do this at 60 gigahertz. So, you say if my modulation bandwidth is only 250 megahertz, how am I going to respond to 60 gigahertz? Well, you just follow this modulation transfer function curve, and you say you go all the way up to 60 gigahertz, you will find that h of f is very small, but it is not 0, right. It will probably be that modulation, that strength of your modulation that you are finally achieving is only in the order of 10 power minus 5 or something, 10 power minus 5, 10 power minus 6, but still that constitutes a very small component that is modulated on a very large DC, right. If it is not getting modulated, it just represents a DC level, right. So, but that is okay, as long as you have in your electronic circuit, you have a filter which rejects all the short frequencies and picks up only the 60 gigahertz component. You can just beat with 60 local oscillator with 60 gigahertz, and you can extract that component, that modulated component, and that is how they are planning to do communication. So, when we say that the 3 dB bandwidth is 250 megahertz, that just says that at 250 megahertz modulation transfer function is 50%. So, only 50% of my light is actually modulated, rest of it is actually a DC level, okay. But still that modulated component you can pick up and you can do things with that, or even if it is F10 dB, F20 dB, corresponding to that you have higher modulation bandwidth, right. So, you can possibly, if you can pick up that modulated component precisely, you can still do at higher frequencies, okay. This is not like a hard set limit to the modulation that you can achieve, it just gives you an idea. Do you understand this? So, the question is the phase nonlinear when you go to even higher frequencies? There is a phase delay, yes, because it is not responding quickly enough, but there is nothing in this that says the phase is nonlinear. The phase will be nonlinear if your modulation transfer function starts actually having some other features in it. It is not a monotonic signature, it starts having some other nonlinearity in it, okay. Then you would have a phase distortion as well happening. But according to the processes that we are tracking here, there is no such nonlinear function coming to the picture. But if there is some other physical effect that is giving you some nonlinearity here in the modulation transfer function, then the phase will also get distorted. Let us look at the other characteristic that we have neglected so far, which is actually the spectral characteristics. So, what about the spectral characteristics of an LED? So, if I have recombination happening from an electron from the conduction band recombining with a hole in the valence band, right. So, what sort of spectral characteristics do I expect? And of course, the spectral characteristics are going to depend on where the electron is, where the hole is, and that corresponding energy is what is going to get emitted. But the spectral the spontaneous emission rate can be tracked as integral of EC to infinity over all these energy levels. E2 corresponds to the energy levels in the conduction band. So, some constant A f of E2, that is corresponding to the probability that an electron is sitting in this energy level E2. This is actually important to remember. I did not talk about it explicitly before. In semiconductors, this Pauli's exclusion principle comes into effect, right, which means that no two electrons can exist in the same state. Okay. So, when we are talking about f of E2, we are talking about an electron occupying a particular energy level, right. And so, you need that, and you also need a hole in the valence band, and that corresponds to, so this is actually the FCE2, and this corresponds to 1 minus FeE1, right, where E1 corresponds to the energy level in the valence band. And then you have the density of states also come into the picture, which can be represented as a joint density of states corresponding to the conduction and valence band. Okay. So, that will determine what is the emission characteristics in terms of the spectrum, and if you evaluate that, that will correspond to some A naught multiplied by the joint density of states is going to be proportional to this factor h nu minus E g to the power of half. So, remember the individual density of states in the conduction band, what is it corresponding to? Rho c, what did we say is equal to? E minus E c to the power of half, and rho v we said was E v minus E to the power of half. That is what defined the individual density of states, but the joint density of states can be expressed as h nu minus E g to the power of half. And then the Fermi probability, when you look at for both of these electron and hole, that will work out to be exponential of minus h nu minus E g divided by kBt. So, both of these essentially say that okay, the spontaneous emission is going to be dependent on this factor of h nu minus E g, right. And okay, so if I plot this spontaneous emission as a function of h nu, what I will see is that it is going to be something like this. wherein you have near the band edge. So, you can say that the emission is going to be happening at a minimum energy corresponding to the band gap energy, right. You cannot have any emission lesser than the band gap energy, because you do not have any electrons and holes within that energy. So, between this is your band gap energy, right. So, you are going to have emission for Eg greater than for h nu greater than Eg, right. And then if you look at where the peak happens, if you differentiate this and with respect to h nu and equate to 0, you will find that the peak, you can show that the peak happens at a point corresponding to Eg plus kBt over 2, right. So, it is just beyond the band edge that you are going to have the maximum. So, this emission cannot be less than Eg, right, and it will peak at a value correspond to Eg plus kBt over 2. So, on the lower energy side, it is dominated, it is decided by this h nu over Eg to the power of half, whereas on the higher energy side, it is going to be limited by the Fermi probabilities. Okay, so that is where that exponential comes into the picture. So, you have a long exponential tail typically, and on the shorter side it is going to be dependent on that square root function. Okay. And in this, one of the important things is what is this full width half maximum, right, FWHM, and that again we are not doing it rigorously, but you can find out from that expression, from plotting that expression, and that you will see corresponds to a value which is given by 1.8 times kBt divided by h. Okay, that will be the full width half maximum of this LED. And interesting thing is you see that all of these are constants, Kb and h is the Planck's constant, so they are constants, but T is the only variable. So, if you look at T equals to 300 degree Kelvin, if you substitute that into this expression, you will find that this delta nu corresponding to the FWHM is about 11 terahertz. Okay. So, at room temperature, all LEDs have roughly a spectral width of 11 terahertz, right. And this 11 terahertz, what it means in terms of delta lambda, in terms of the wavelength spread, obviously depends on what wavelength you are operating at. So, if you are operating at 1550 nanometers, you will find that the wavelength spread corresponds to about 100 nanometers. If you are operating at 1 micron wavelength, that wavelength spread will be more like 40 nanometers or so. Okay, and of course, if you are around the visible region, that may be even smaller, okay, in terms of delta lambda. But delta nu, you can say that it will correspond to 11 terahertz if you are operating at 300 degree Kelvin. Okay, so that is another interesting aspect. So, we say that all these LEDs, what is the primary emission wavelength? We said it is gallium nitride based LEDs. What can you say about their emission? No. These are actually UV LEDs, ultraviolet LEDs, okay. And we can actually show this to you. If the TAs can remember, can we just bring our spectrometer? We have that Maya spectrometer, or some spectrometer, visible spectrometer is there. So let's bring that and let's examine these LEDs. What you will find is this is actually emitting in the UV radiation, right? It's emitting UV radiation, and you can say if it's ultraviolet less than 400 nanometers, the spectral width there corresponds to only a few nanometers, okay, only a few nanometers. And how are we getting white light which is spanning 400 to 700 nanometers? It's because each of those LED elements, there is actually a phosphor coating on it. That phosphor coating gets illuminated by UV light, just very much like your old fluorescent lamps. You know, you will have a phosphor coating on the inside, so you will emit white light. So similar case, it's excited by UV radiation, but it emits white light. Now I will be interested in knowing how much UV light is not getting converted, how much UV light is coming through this, and how much UV light am I getting exposed to. I would want to know. So let's actually bring that spectrometer and check this light to see this. So yeah, there is a conversion efficiency involved. So there are some photons that could be scattered and not really going through that conversion. So there is a conversion efficiency involved, but I believe the conversion efficiency is greater than 50%. But depending upon the thickness of the phosphor coating, you may or may not absorb all the UV radiation. So I'm fairly sure I'm going to see a UV component coming out of this, and I'm actually curious, as you are, to find out how much of that UV component is coming through. Okay, so let's stop at this point. What we will do, next is actually look at similar characteristics for semiconductor diode lasers, but knowing all the laser characteristics that we already have discussed in rare earth systems, I'm not expecting to spend a lot of time on that, and then we'll go on to semiconductor light detectors. Okay, thank you.